These are some notes that will help us for the topics that we need to learn in lecture 6. So the first tool is about integrals, and the two types of integrals that we have in this course are proper and improper integrals. So far we were working only with proper integrals, and that is for a function f of x defined on an interval ab. We have this definition of what an integral is, like a proper integral. So the integral from a to b of our function f is equal to this capital F of x, and we have to evaluate this capital F in b, and then that value minus capital F at a. So, and this capital F is an antiderivative for little f. That is that if we compute the derivative of capital X, then we recover little x. Okay, so that was the type of integrals that we were working before in the course. And here we have just a graph. If we have this function f here, and this is f of b and f of a, then this integral in this case for this positive function means this area under the graph of f. But okay, this is not super important, just we are going to see the difference between proper integrals and the improper ones, that are the new part, the new type that we are going to work with in this lecture. So imagine that we have our little f, but defining on this interval open in A and closed in B. So that means that we know that f is well defined for any c between a and b, but strictly larger than a. So when we write this, which is exactly the same notation that we were using for proper integrals, when we write this, in this case where we don't know if f is defined at x equal to a, what we mean here is this limit. So we know that for every c strictly greater than a, f is well defined. So we can compute this piece of integral between this any c and b, and then to get this value, this notation, this is the definition, we just take the limit of c approaching a from above. Okay, so let's see this graph to have an idea of what we are talking here. So here we have an f defined here in this b, and it's well defined in all these values, but it's not defined here in a. Okay, so we can compute this integral for any c, and that's what we do, and then we take the limit approaching a from above. So this is one type of an improper integral. Okay, this problem in A can be also found in B, in the sense that, okay, now we have a function f defining on this interval closed in A and open in B. Again, we don't know what's going on in B because maybe the function is not defined there, but we can compute this integral of f between a and c for every c strictly less than b. So we compute this, and then again the same notation that we were using for proper integrals, but now the meaning of this notation is just taking the limit of all these possible values c approaching b from below now. Okay, this is just a definition. This is another type of an improper integral. So we have a picture here. Imagine that we have this f, which is defined in a and in every value here, but not in b. And okay, so we can compute this integral as the limit of the integrals of, let's say, c here, strictly less than b. But okay, then we can take any c, and that taking that any c means that we are taking the limit when c approaches b from below. Okay. So these two guys, when the function f has a problem in a, or when the function f has a problem in b, where having a problem means that maybe it's not well defined, like here we don't have f of b. Okay, so when we have this situation, these two integrals, which have the same notation as before, mean this taking these limits, okay, and they are improper integrals. Okay, more examples of improper integrals. When this a is minus infinity or b is infinity, we have also improper integrals. And how do we understand this notation, the integral from a to infinity of f? Okay, well, that means you start in a and you have f of x for every x greater than a. So you can stop in some value m, and you can compute this integral from a to m as a normal one, as usual integral, like a proper one. And then, okay, but you wonder what is going on in infinity. So then you take the limit of m going to infinity. So what we have here is exactly this graph that we have next to the definition of the integral. So we have a function f, we have a starting point a, and then we have infinity, let's say, which is like here, right, in the future, let's say. So this integral for a positive function, for example, means that we are computing this area under the graph of f from a to forever, to infinity, okay? And this is the definition. So we cut in certain m, but then since we want the value going to infinity, let's say, then that means that we add this limit here in the front. Okay, so this is another type of improper integrals, and we will need this notion for lecture 6. Well, as you can imagine, if now a is minus infinity, the only change is that we kind of change the direction. So minus infinity is here, and we wonder what is this notation, the integral from minus infinity to b of f of x. Okay, so that is, well, here we have an f, and here we have the value of f of b, and then we have some minus m here, so we for sure can compute this proper integral as usual. And then since we want to know what's going on in infinity and minus infinity, we just make this m go to minus infinity, and that's exactly what this notation means. Okay, so those are our improper integrals. And one more definition, if we have both extremes of the integral equal to infinity, like minus infinity and infinity, here in this course, there are more ways to define this, this notion, this notation, but here in this course, we are going to take this definition. So we have an m, positive m, and we compute the proper integral from minus m to m of f, and then we make m goes to infinity. And that's the definition for this last improper integral. Okay, so here we have a picture. So this is our f of x. Here we have a positive m and his friend here minus m. So we can compute this proper integral for every m. And then since we wonder what's going on in minus infinity and infinity, we just make this m goes to infinity. Okay, so maybe some examples to fix ideas. Okay, first one. Here we have the integral from 0 to 1 of this f. And okay, this f is well defined when we are not exactly 0. So for every z1, for every c greater than 0, we are okay. So we can compute this integral on every interval of this form where c is strictly positive. But we cannot compute f of 0 in this case. Okay, so this integral is an improper integral because we have a problem here. Okay, so by definition, the definition that we just gave, this integral means, okay, you can compute these integrals as usual because they are proper ones, they are well defined and everything is okay. But then your real intention is to compute this one with the 0 that you don't know because f is not well defined there. But okay, the definition says, don't worry, compute these integrals for every c greater than 0, and then just take the limit and see what happened. Okay, so this integral is exactly this logarithm, and we have to compute this between 1 and z. And what we get is this value. This one is equal to 0, so we get this minus logarithm of c. And this guy, only the logarithm of c, goes to minus infinity. If you remember the graph of the logarithm function, is like that. And with this minus in front, that what we get is just infinity. So this improper integral takes the value infinity. So we can say that diverges, but okay, it's not important to say if converges or diverges, it's important to know how to compute them. Okay. So, second example. Now we have this type of improper integral where the extremes are infinity, minus infinity and infinity. So here the previous example was like, okay, this in principle looks like a proper integral, but the problem is that this function is not well defined at 0. So this is also an improper integral, no matter that it looks like a proper one. And okay, this looks like an improper one because the extremes are already infinity, equal to infinity. Okay, so by definition of this course, remember there are many ways of defining this guy, but in this course we will take this definition. We have to compute this proper integral for every m positive, and then we just take the limit when m goes to infinity. Okay, so an antiderivative for this function is, okay, we can observe that this function is even. You can check that, but it's due to this square here, so minus x squared is the same of x squared, and then we have that this function is even. So we can rewrite this guy as 2 times the integral from 0 to m of the same function. That's because we have an even function. Okay, and now an antiderivative of this function is the inverse function of the tangent of x. And if you remember how the graph is, it's like that. And okay, now we have to compute this at m, at this at 0, and subtract this at 0. So at m, I don't know, m maybe is here, so we have this inverse tangent of m, which of course we cannot really say the value because we don't know who which value takes m. It's just a general variable for us now. And then we have the inverse tangent of 0, which is 0. So we have 2 times this is 0, so this is the term that survives. And now if you look at the graph, and here was our m, and then m goes to infinity, then the graph of the function is going to pi over 2. So that's the limit when m goes to infinity. So coming back to the computation of the limit, this guy, when m goes to infinity, goes to pi over 2. So that's what we have here. And so these two and these two kill each other, and we have pi. Okay, so this improper integral takes the value pi. We can say that it converges, but okay, again, doesn't matter we are not going to, we are interested in computation, so it doesn't matter if the words diverges or converges. Okay, so that was the first important tool for lecture 6. Second important tool is this L'Hopital's rule to compute some limits. So we want to compute this limit. We have two functions, f of x and g of x. And okay, we need to compute this limit when x goes to c. And we have some assumptions of these guys, f and g. What's going on with them is, okay, both of them goes to 0, like they verify these assumptions, like when we take the limit of x going to c of f, we get 0, and of g we get 0. Or when we take, so this is a package that comes together, let's say. Or the other situation could be this, where the limit of f of x when x goes to c goes to plus or minus infinity, and the limit of g of x when x goes to c goes to plus or minus infinity. So in these cases, so again, we need to compute this limit, and f and g verifies these conditions or these conditions. So don't mix like, oh, okay, so f goes to 0 and g goes to infinity, because then you are not allowed to apply this rule. So the rule only works when you have this situation or this situation. So make sure you don't mix the assumptions. Okay, so in that case, this rule says that, okay, why don't you compute this limit? You differentiate f, differentiate g, and then compute this limit instead of the original one with f and g. Then, if that limit exists, then you can say that both coincide. And this is the rule that we are going to use also in lecture 6 in some cases. Okay, so remember, if f and g verifies one of these two assumptions, both go to 0 when x go to C, or both go to some infinity plus or minus when x goes to C, then we can compute this other limit with the derivatives of f and g, and they will coincide. Okay, that's the rule. Let's see some example. We want to compute this limit, sine of x over x when x goes to 0. Okay, so this is our function f, sine of x, and g is just x. So it's clear that we have, let's say, the first package of conditions where the limit of x when x goes to 0, which is the limit of sine of x when x goes to 0, is 0. And of course the limit of g of x, which is just x, when x goes to 0, goes to 0. So we are under the assumptions of this rule. So we can compute this auxiliary limit, not the original one, let's say, with the derivatives of f and g. So when we differentiate sine of x, we got cosine of x, and when we differentiate x, we get this 1 here. And this limit exists because now when x goes to 0, cosine goes to 1, and 1 is just 1, so the number 1 is just fixed. So this limit takes the value 1. So the rule says, okay, you have these two functions with these two assumptions, like both go to 0 when x goes to 0. Then you compute this auxiliary limit with the derivatives, and you get a value. And now, since this limit exists, you can claim that these guys coincide, are equal. So your original limit is exactly this auxiliary limit with the derivative of f and g. Okay, so our goal was computing this limit, which is exactly this with our notation of f and g. Thanks to the rule, we have this identity here, so this limit is exactly 1. Okay, and that's it for these notes, where we just saw two important tools for lecture 6, which is the definition of improper integrals that we are going to work with, and this rule to compute some limits of functions when we are in certain situations, which were these two situations. Both functions, f over g, we have a limit f over g, and both functions had a limit going to 0, or both functions go to plus or minus infinity. Okay, so now I think we are ready for our actual lecture 6.